Hello, this exercise 21A, as the title suggests, we're resolving forces and looking at magnitude and direction of that resultant force. Now this should be something we are getting quite good at doing. I mean, magnitude and direction straight away makes me think of Pythagoras and trigonometry, for instance. So this should be fairly familiar, but obviously now we've got potential for vectors. And you'll notice a starter immediately is in vectors as well. Three horizontal forces act on a particle. In newtons those forces are. So again, I prefer much better if I write F1 is 2I, so that's just 2 naught. F2 is 3J, so that's 0 3. And F3 is I minus 2J, there you go. Calculate the magnitude and the resultant of the resultant force and its angle from the direction. So the resultant force is just overall forces. These all added together, I reckon that's 3 and 1. So if I just draw that little triangle, obviously 3 across, 1 up. So by Pythagoras, the magnitude of this is 3 squared plus 1 squared is 10, so it's root 10 is the magnitude. And the direction, which I'm going to, it says to the I direction, which is obviously, this is I, it's the X direction. So that angle there, I'm going to say is alpha, is the inverse tan of 1 over 3. Always do with y divided by x. So inverse tan. Need to make sure I'm in radians at the moment, so let's get out of that. In degrees, inverse tan of 1 divided by 3. Now I get 18.4 degrees. So it's quite straightforward, that question. Fingers crossed I've done it right. A force of 40 newtons acts at 30 degrees to the horizontal. So presumably something like this is my 40 newton force. And then to the horizontal it's acting at 30 degrees. Find the horizontal component of the force. Well, you should by now know to resolve that, you go, whenever it's the cross one and it's the angle to the horizontal, it's 40 cos 30. So 40 times cos 30, I get 20 root 3 or 30.6 newtons. Give or take a bit. So 18.4, 3.16, that was root 10 presumably, yes that's right, and 34.6 newtons, good. So some examples then of what we're doing today. We've got 3 angles acting at a point, and I need to combine these 3 forces. So it's a bit of what I've just done, just sort of all joined together. So if we write out each force, the overall force again, well let's do the easy ones. That 3 newton one is minus 3, 0, plus the other easy one is this one that's down, so it's 0 across 14 down. And this third one, well, just be aware it's going in the I direction, it's 10 cos 25, and in the J direction, it's 10 sin 25. And once you've realised this, it's coses across and sines up and down. As long as they give you the angle, to the horizontal, this is relatively easy. 10 cos 25. Don't forget to take away the 3 from before. I get this to be, I'm going to give it to a couple more dp's than I need. 6.0631. I'll do the other one. It's 10 sine 25. Take away that 14. More going down than up. And that's minus 9.7738. So now I know those. Overall it's going across 6 and a bit. It's going down 9.77. And that allows me then to work out my angle and my resultant. So I'll do that now. The resultant using Pythagoras will be that answer squared plus 6.0631 squared, and then 132ish square root the answer. I get 11.5236 figs. And my angle, which I'll call alpha, is the inverse tan of 9.77 and a bit. I'm going to use the as accurately as I can, divided by the 6.06. So what is it? It's 9.7738 divided by 6.0631. Inverse tan that answer. I get 58 degrees. I've got 58.2 degrees to one significant, three significant figures. I'm going to say below the horizontal. So just to highlight the fact that it's gone underneath and not above. 58.2 and 11.5. Good, we're all happy with that. Notice I split it up when I first did it as a top line and a bottom line. I called it a resultant in the x direction and a resultant in the y direction. But actually writing it in these vector notation is probably a neater way to do it. A particle is acted on by two forces, F1 and F2. Alright, and so if I just draw this, it might help actually. So it says minus 10 plus 6. So there's that's my F1 force. Now my F2 force, it says, is on the bearing 150. Don't forget that bearings are different from normal angles in maths. Bearings start from the north line. So that's the north line there. And therefore it's a bearing coming round here at 150. And I suppose the fact that that's 150 and that's a 90-degree angle, well, that tells me that this is 60 degrees. So let's bear that in mind. So it's somewhere going down there. I don't know how far. That's F2. And so I just need to bear that direction of those two things in mind. So my resultant force is Fe equals, what was it, minus 10 and 6, plus my second force was, well, it's going across. So cos is across, still works, still angle to the horizontal, admittedly it's underneath the line. So what was it? It was a length of 4. So I'm going to say it's 4 cos the angle to the horizontal, which I think is 60 degrees. That angle there is 60. And going, well, it's going down, so it's definitely a minus, and therefore it's minus 4 sine 60. So if I do those numbers, so what is it? Let's just type that in. Minus 10 plus 4 cos 60. I get minus 8. And 6 minus 4 sine 60 won't be quite so pretty. Sine 60 is not a nice number. 2.54, I suppose, to three significant figures. And it's positive. It is positive overall. Give the resultant force. Oh, right. So it just wants it then equals minus 8i plus 2.54j. Just write newtons at the end of it. Well, they've drawn their first force, minus 10i plus 6j. They did separately, which is fine as well. I think mine's neater in vectors again. And what's their answer? Yes, they got the same answer as me. An equilibrium of forces then. Sometimes we get told that vectors, forces are in equilibrium. That means forces left equals forces right, forces up equals forces down. And sometimes it allows you to find a force that they've not told you. So in this question here, we've got three forces. Notice P and Q, there's two forces they've not told us. But we can still find them, basically because left equals right, up equals down. So let's just write it. Overall force. Now, notice it's an equilibrium. So that means the overall force is there isn't one. There is nothing. So I'm just going to write this as three forces. The first force I'll do is P. P is easy. I'll say that's P across, naught up. Plus, well, the second force is also easy. It's naught across, Q down. So minus Q. And plus my third force, well, just be aware, that's 60 degrees. I'd never like these 60 degrees to the vertical. I'm going to call that 30 degrees to the horizontal. And then I can use my cos as a cross rule. So it's minus 12, because it's going left minus, and then cos is across, cos 30. And it's going up, so it's 12 sine 30. And that equals 0, 0, because it's an equilibrium. So look out for this equilibrium. It makes life a lot easier. And the top line then must equal 0. So P minus 12 cos 30. What is 12 cos 30? 12 cos 30. Not very pretty. 10.39. Or 10.4, I suppose I'm going to write it as, equals 0. So therefore P equals 10.4. And the bottom line says minus Q plus 12 sine 30. Well, 12 sine 30 is easy, 6. And that is equal to 0 as well. So Q equals minus 6. Or Q equals plus 6, even when I move it over. Both of those in newtons. 10.4 and 6. Yes, it's worked. Again, this next question looks like it's in equilibrium again. So let's just go through the same process. We'll do this one first. This is 7 and 0. So that's a nice easy one to write down. The vector going down f is fairly straightforward. That's 0 and minus f because it's going down. And the only one I care about, now look, this is a bit, now I've said to you, last time we got a dodgy angle there, I said, well, just find this angle here instead. But it gets more complicated when that's theta. It's harder to write 90 minus theta and still have something decent. So just be aware, when you got the angle to the horizontal, you do cos for the I, and you do sine to the j. But if you get the angle to the vertical instead, you can just switch those around. So I can just go, well, let's just do the sine for the I and the cos for the j. And so in this case, because they've given me theta into the vertical, I'm going to write 15. I want to write cos, but it's the wrong angle, so I have to write sine. Yes, that's right. And notice also, actually, I nearly missed this. It's going left, so I need a minus in there. And going up and down, it is going up, so it's going to be 15. It's going up, it should be sine, but they're giving me the wrong vertical, the wrong angle. So I'm going to write cos theta. And that equals in equilibrium, so therefore equals 0, 0. Top line, minus 15 sine theta, don't forget that 7, equals 0. So said differently, I suppose, 15 sine theta is equal to 7, or sine theta is 7/15. So I'm just going to do the inverse sine of that. The inverse sine of 7 divided by 15. I get an angle for theta to be 27.8 degrees. And what about the f? Well, now I know the theta, I suppose I can do that. I can write minus f plus 15 cos theta equals 0. I suppose f equals 15 cos, well, I know what my angle is now, it's 27.8, but I'm going to use the exact number that's still in my calculator, which is 27.818. So if I do 15 cos answer, that should give me the right answer. 13. It might not have made much difference, but it might do, so you might sometimes be a little bit out, so you should always try to be a bit more accurate if you use an answer. Again, I get 13.3. Perfect. And an example here, I don't think necessarily we're going to get time to do it, so it might be a good question to leave for the class when we go through this in class, and then it's the finally we'll go on to the textbook. Okay, thank you very much.